Yeah, hello everyone. I am Dr. Chander Pawar. I did my MSc, MTech, PhD from Hyderabad Central University, which is India's most premier institute, which is located in Gachibowli, Hyderabad. Belongs to Telangana state. And after doing my PhD from Hyderabad Central University, I moved to China for my postdoc, first postdoc, Zhejiang University, which is world 45th rank. And after doing 2.5 years of postdoc in the China, I moved to Texas A&M University for my second postdoctoral research. And after doing 1.5 year research in the Texas, I moved back to India, and then I joined as a associate professor in the Mlritm college. And here today I am here to present engineering chemistry, which is part of a BTech system. So there are 5 modules, water and treatment, battery, corrosion, and polymers, and energy materials, and smart materials. So now basically I will be discussing something about first module, that is water and its treatment. Before that, going into their details, basics of chemistry. Chemistry is certainly called as a central science. Why? Because it combines maths, physics, biology, everything, even including engineering. And basically chemistry deals about the properties of material, its composition, structure, formula, etc. And Anton von Laurent Lavoisier is the father of chemistry. Why? Because he has named oxygen and hydrogen, which are most prominent elements in the periodic table. Now coming to atom, atom is the building block of material, and this is the basic unit which we know to know about chemistry. So atom is nothing but very beautiful definition is invisible, indivisible, indestructible. Ultimate atom is called as a ultimate particle is called as atom. So basically that's a very nice definition. Invisible, which we cannot see with our naked eye. Indivisible, we cannot chop or divide further. And indestructible, which we cannot destroy. So ultimate particle is called as atom. That's a really very beautiful definition, and this is the building block of material what we see today, universe existing based on the atom. And if we go further detail into atom, electrons, neutrons, protons, nucleus, positive charge, all these concepts comes. So now here our first module, as part of our BTech system, first module is water and its treatment. Water, we all know that it's a combination of two molecules of hydrogen and oxygen, which we represent H2O. That's a basic formula of water. Why we need to study about water? Why? Because water is most abundant and most essential component for the living beings. So that's why we need to study. Why? Because in every sector, agriculture sector, sanitary sector, industrial sector, for bathing, clothing, everything, for everything, water is essential. So that's why we need to know something, some properties about water, why it is essential. So that's a basic information. And now water, basically there are 3 impurities in the water: physical impurity, chemical impurity, and biological impurity. Physical impurity, based on whenever rain comes, generally sleet and plant leaves, any other garbage, this that will floats, and it will go to tanks and lakes, rivers, etc., which is a physical impurity. It causes physical impurity. And when we talk about chemical impurity again categorized into cationic and inorganic and organic impurities. So inorganic impurities again categorized into 2 types: cationic and anionic. Cationic, like cations like metal ions, Al plus, Fe2 plus, Fe3 plus, zinc 2 plus, all these metals which are positive charged cations. And anion based impurities like sulfate ion, SO4 2 minus, Cl minus, chloride ion, F minus, fluoride ion, and nitrate ion, NO3 2 minus. All these negatively charged are anion based impurities. And when we talk about organic impurities like pigments, dyes, petroleum products, wastage, all these comes under organic impurities. And final third one is biological impurity. Biological impurity, pathogenic water, which is having pathogenic bacteria, fungi, algae, viruses. So that is related to biological impurity. So these are the broadly 3 impurities which are present in the water. And here we can see Hardness of water. Why water is becoming hard? Because when rains, water flows from the rocky, rocky areas, this that. So when it flows from the rocky, for areas, whatever the hardness causing salts are there, those will be merged with the water, and ultimately it lead to hardness of water. When we talk about Nalgonda district in the Telangana, there is a huge groundwater with a huge fluorosis, fluoride content. So then that water is we cannot drink. It cannot be used for drinking purpose. Why? Because fluorosis. Fluorosis. It's a disease which causes organ disorders. Disabilities, many disabilities. So basically, so hardness of water is categorized into two types, soft water, hard water. Soft water, when we talk about soft water, water with soaps. Soap is nothing but higher fatty acids. Sodium stearates are, potassium and sodium based salts. Soap is nothing but, whatever we talk about, Medimix, this, that, Lux, this, that, Santur, these are brand names. But, generally the chemical composition is nothing but higher fatty acids of stearic acid. So when we interact this soap with water, if that gives, upon interaction, if that gives leather formation is nothing but, foam formation, then that will be considered as a soft water. If the interaction between the soap and water doesn't give leather formation, foam, then it will be considered as a hard water. Here we can see the formula of sodium stearate, C17H35, and COONA, sodium stearate soap, and water, which gives stearic acid and water. So that is the soft water. Whereas in the hard water, there is no such stearic acid formation. There is a calcium and magnesium based complex. That means it is not giving the foam, leather formation. So it is considered as a hard water. Now, yeah, temporary hardness can be removed by the simple boiling. Why? Because temporary hardness mainly because of the bicarbonates of calcium and magnesium. You can see here calcium HCO3 taken twice, or magnesium HCO3 taken twice. These are the two calcium and magnesium based bicarbonates which are responsible for the temporary hardness. So temporary hardness can be removed with a simple boiling method at higher temperatures. When we talk about permanent hardness is caused due to the chloride ions, fluoride ions, sulfate ions, nitrate ions, etc. And permanent hardness cannot be removed by simply boiling methods. So here we can see calcium chloride, CaCl2, MgCl2, and calcium sulfate, magnesium sulfate. All these are the permanent hardness causing salts with the form of, with the help of calcium and magnesium metals. Now, this permanent hardness cannot be removed by simple boiling, and we need some chemical treatments to do purification of water. And this total hardness can be calculated by the simple formula, that is molecular weight by weight of salt by weight of the salt by molecular weight of the that corresponding salt. Now, let us see here. There are some units to represent the hardness of water, and basically ppm, parts per million, that is the first unit to represent the hardness of water. Second one is mg per liter. Mg per liter is milligram per liter. And then degree Clark and degree French. These are the 4 units to represent the hardness of water, and there is a relation between these 4 units. 1 ppm equals to 1 mg per liter equals to 0.1 degree French equals to 0.07 degree Clark. This is the relation between these 4 units of hardness of water representation. Now, if there is a problem here to calculate the total hardness of a given water sample. Here we can see a sample of water gives an analysis of 13.6 mg per liter of calcium sulfate. Calcium sulfate is a permanent hardness causing salt, and 7.3 mg per liter of magnesium bicarbonate. Magnesium bicarbonate, it's a temporary hardness causing salt. So there are 2 salts. One is calcium sulfate, permanent hardness causing salt, and magnesium bicarbonate, which is temporary hardness causing salt. The permanent hardness causing salt weight is 13.6 mg per liter, and permanent temporary hardness causing salt magnesium bicarbonate, its molecular weight, its weight is 7.3. Now we can see simply when we calculate weight by molecular weight. For example, calcium sulfate, when we talk about calcium sulfate, calcium, its atomic number is 20 and mass is 40, and sulfur, so 40, sulfur atomic number is 16, mass is 32, so 32, and oxygen, there are oxygen atomic number 8 and mass is 16, and 4 into 16, 64. So here we can get 136. That is the molecular weight of calcium sulfate. So now weight is already given for this permanent salt. So let us calculate weight. How much? 13.6 grams by 136, which is a molecular weight, and weight by molecular weight into 100. Then we will get 10 ppm. 10 ppm parts per million. This is the permanent hardness for calcium sulfate. Now let us calculate the hardness of temporary hardness of a given salt. Now what is the salt given? Magnesium bicarbonate, MgHCO3 taken twice. Now you can see what is the weight of this temporary hardness causing salt, 7.3, and its molecular weight is 146. So into 100 equals to, we will get somewhere 5 ppm. So now the total hardness of water is TH. TH is total hardness. Total hardness equals permanent hardness pH plus TH, temporary hardness. Permanent hardness is 10 and the temporary hardness is 5, equals 15 ppm. So now the total hardness is 15 ppm. Now let us see. That is about the formula, problem for the hardness calculation, total hardness calculation. Now EDTA is the most essential method to calculate the total hardness of water. EDTA method, complexometric method. Why we are calling it as a complexometric method? Why? Because ethylene diamine tetraacetic acid. The structure of EDTA is CH2, CH2N, CH2, COOH, CH2, COOH, CH2, CH2, COOH. Now you can see here, ethylene EDTA is called as a hexadentate ligand. Why? Because there are 4 acetic acid groups. Upon removing the proton, they will become acetate ion. So there are 4 acetate groups, and there are 2 amine groups. Okay, 2 amine groups. So total there are 6 electron excess elements. That's why we are calling this EDTA as a hexadentate ligand. What it does exactly? Whatever the hardness causing metals or salts are there in the hardness causing water, it will make a complex with the help of calcium and magnesium which are there in the water sample. It will make a complex, and then we can find out how much calcium ions are there in the given sample. So, and this is called as a volumetric analysis method. Here you can see the structure of EDTA, 2 ethylene, ethylene CH2 group and 2 amine groups, which is functionalized with 4 acetic acid groups. And here, so basically for this method, we use titration method, complexometric titration method. In burette, we have to take the EDTA solution which we have prepared in advance, and then in conical flask we have to take the tap water, or whichever the sample you are going to measure the hardness of the sample. It could be any area from the Hyderabad, Kukatpalli, or Dundigal, or any area water sample. 20 ml you have to take into the conical flask. To that you have to add buffer. Buffer is nothing but here ammonium chloride and ammonium hydroxide, which is represented here. So the main role of this buffer is to maintain the basic pH. You can see here basic pH. And why we need to maintain the basic pH? To make a complex with the hardness causing salts, and to that we need to add at least 2 to 3 drops of EBT. EBT is nothing but eriochrome black tea. That's an indicator. Okay. So when we add this, EBT indicator and buffer to the conical flask, initially it will be appearing like, wine red color as it is represented here. And when we do the titration with burette filled EDTA, so at certain temperature, readings, that will be turned into blue color. Once it is blue color changed, then we have to stop the titration and we have to note the readings. So likewise, we have to repeat it thrice, and then we have to take the average of these 3 readings, and with that we have to use the further permanent hardness calculations by using the M1V1 equals to M2V2 formula. Now we can see potable water. What do you mean by potable water? Potable water is nothing but water which is readily available for the drinking purpose. That means simply drinkable water is called as potable water. Pot we use for the drinking water. So pot to potable water. So there are certain specifications for the drinking water. What are the specifications? So first one is TDS. TDS is nothing but total dissolved solids. TDS should be less than 500 ppm. The total dissolved solids in the water sample should be less than 500 ppm. Second thing is that there should not be any carcinogenic or harmful metals like arsenic, lead, manganese, chromium. All these metals should not be there in the drinking water. And thereafter, the color should be clear, and it should be odorless and pleasant taste. Okay. And thereafter, the optimum hardness of must be less than 125 ppm for the drinking purpose. And then pH of the potable water should lie in between 7 to 8.5, and the drinking water turbidity should not exceed 25 ppm. And it should be free from the pathogenic bacteria. There should not be any virus, fungi, algae, bacteria in the drinking water. These are some of the specifications which are very, very important to understand what are the specifications for the drinking water. Yeah, for this potable water, we have several steps to treat the water. So first one is source of water. It could be rainwater, it could be river water, it could be lake water, it could be groundwater, whatever it may be. So first step is screening. Screening is nothing but there are several steps: screening, aeration, sedimentation, coagulation, filtration, and disinfection. So these are the steps involved in the treatment of potable water. To make the water drinkable, so we need follow these steps. So screening is nothing but, so whatever the larger or bulk particles are there, garbage, we have to remove those, and it can be done by the simple screening method. Okay. And then aeration is nothing but whatever the carcinogenic gases like carbon monoxide, hydrogen sulfide, carbon dioxide, these gases will be air blown, and these toxic gases can be removed by the aeration method. Means we flow the water, and against to that water perpendicularly we will be sending the aeration gas, which can be removed by which can remove the oxygen, hydrogen sulfide, and carbon dioxide related toxic gases. And then sedimentation is very simple. We have to keep our water whichever we are using for the treatment, so keep aside without any agitations, without any vibrations, without any disturbance. So what will happen, whatever the larger particles or whatever the impurities are there, those will be settled down, and then we have to keep it for something like 2 to 5 hours. Then whatever the impurities are there, those will be settled down. Once it is settled down, we have to use that sample for the coagulation. Coagulation is nothing but aggregation of smaller particles, nanoparticles. So coagulation generally we use for the aggregation of nano microparticles, and then we will do the filtration. Filtration generally can be done in 2 ways. Yeah, in 2 ways. There are several layers in our setup. So upper layer will be sand layer. Sand layer, since sand means silica, which is having micropores. So whatever the impurities are, whatever the nanoparticle impurities are there, those will be absorbed into these sand pores. And then further is gravel. Gravel is something like 20 mm of tiny stones. So minute, very minute nano, pico, femto nanoparticles will be adhered on the surface of these gravels. And finally, third step, we will be getting the sorry, we will be getting the potable water. These are the several steps for the treatment of potable water. So now the interesting part is that after the potable water, filtration, the major treatment method is disinfection. So disinfection can be done in three ways. First one is by addition of chlorine gas. Okay, chlorine gas to our water which we are going to do the disinfection. So chlorine gas, that is chlorine gas directly sending, that is first method, and then chloramine sending. Here we can see chlorine with water. Chlorine with water forms HOCl, hypochlorous acid, and this is the main which we need to obtain in the reaction. Once we get the hypochlorous acid, this hypochlorous acid HOCl can be further dissociated into HCl and nascent oxygen. This nascent oxygen generation is very important when we do the treatment of or disinfection of water. Now see, we can see the beauty of this nascent oxygen. Here we can see by adding chloramine, chlorine plus amine chloramine, that is ClNH2, and then this further chloramine will be interacted with water which forms hypochlorous acid HOCl, we can see here, and hypochlorous acid further upon dissociation HCl and nascent oxygen. First case, first to chlorine and chloramine, in both the cases hypochlorous acid formation leads to HCl as a byproduct and nascent oxygen generation. So that is the first method, chlorine. Third method is ozonization. Ozonization is nothing but O3 conversion into oxygen and nascent oxygen. Nascent oxygen can be always represented into square brackets, as I represented here, square brackets. So third step is adding bleaching powder. The formula of bleaching powder is CaOCl, and with water. Calcium hydroxide will be first product, chlorine another byproduct, and hypochlorous acid which we want. This is desirous, HOCl. This HOCl further dissociated into nascent oxygen and HCl. The nascent oxygen generation is very important when we do the disinfection of water. Why? Because this nascent oxygen is strong oxidizing agent. That's the first point we need to consider. Monoatomic in nature, highly unstable, and it kills the bacteria. How it kills? Due to its highly unstable nature and strong oxidizing nature, it easily penetrates into the bacteria and it leads to the rupture or killing of the bacteria. That's why nascent oxygen generation is very, very important when we talk about the disinfection of water by using the chlorine gas, chloramine, ozonization, and by addition of bleaching powder. So these are the three major steps which are essential for the treatment of water for the drinking purpose.